All right, so today what we are going to be looking at, alkanoic acids. All right, so alkanoic acids. So for you who have your concise, we're on page 143. Page 143. I think the if you have the old concise, it's supposed to be there as well, as you just find alkanoic acids. I don't know what exactly page it is on, but you should find alkanoic acids, and we're going down from there. So I'm going to hit some position. All right. So, all right, Akela, I see you come back there. But we are recording just in case. All right. So what we have.
Thank you.
Okay. So what we have today is alkanoic acids, or we also know it as carboxylic acids. Can someone tell me what is the general formula for an alkanoic acid? Anybody? What's the general formula for an alkanoic acid? If I could pull somebody in. So I encourage you all to be bold. Remember the general formula? Let me see if Diamond there. Diamond, you there? Remember the general formula for an alkanoic acid? All right, so I'm not getting Diamond. What about you, Kishona? All right, Shaniqua. Go ahead, Shaniqua.
So CnH2n plus 2 COOH.
CnH2n plus 1 COOH. That's what you said, right?
Yes, sir.
Right, that is correct. Okay, so CnH2n, all of them starts with that, CnH2n. All right, plus 1 COOH is the one for alkanoic acids. All right, another word for alkanoic acids, we just call them carboxylic acids. That's another word. So AKA, also known as. All right. So they are represented by a group. This group is all known, which is called COOH, and that is called the carboxyl group. All right. Carboxyl group, that's COOH. If we had to draw it out in terms of structurally how it looks, it is connected to an R. When we see that word R, and you'll see sometimes in some of your book, you'll see R, COOH. R represents the carbon chain that it is connected to. And R could be any length. It could be 1 carbon. It could be 5 carbons. It could be 20 carbons. All right? But it's just 20 carbons connected to COOH. Or 2 carbons connected to COOH. R could be any number of carbons. So R connected to carbon double bond to an O, and we have OH. All right, that is how the structural formula of the carboxyl group it is in. Of course, we just put OH, but that means that there's a bond here between oxygen and hydrogen. All right. Sometimes we just put OH because it's already understood that they are bonded singly to each other. All right, that is just in case. So what do we know about alkanoic acids? They are polar in nature, right? Last time we would have explained what polar means when the oxygen, which is the electronegative part of the molecule, pulls electrons to itself, it makes the hydrogen exist as a positive charge. And as a result, they have this polarity, going which are negative and a positive end. And as a result, we call the molecule polar by nature. Then that is because of the OH group. So because of that OH group or hydroxyl group, it is going to be polar. All right, so like alcohols, the same alkanoic acids, they are more volatile, or they are less volatile, not more, less volatile than alkane counterparts or corresponding alkanes. So the less volatile, which means that alkanes have an ability to evaporate much faster than they do, but alkanoic acids do evaporate. That's why if someone takes vinegar, which is an alkanoic acid, and throw it on the floor and you enter into the room, you're going to smell, and you're going to say, I'm smelling vinegar. Or if someone put vinegar in a pot where they're cooking, you'll be able to say, I'm smelling vinegar, all right? Because vinegar or the alkanoic acid is a volatile substance, therefore it can change from a liquid to a gas quite easily, all right, without boiling. So in addition to that, they are soluble in water. And all of this is these are the physical properties, eh? All of this that's the physical properties of the alkanoic acids, physical properties, because they're not reacting with anything, it's just how they behave. So I take an alkanoic acid and I put it in water, it's going to dissolve. That's why ethanoic acid, aka vinegar, is soluble in water. Okay. And one thing, the last thing, they dissolve in water. So we know that they're soluble, but they become an acid. All right. So they partially ionize. In water, all right, forming weak acids. So they are weak acids, all right? So we have a formula here, CH3COOH, all right? And it's aqueous form, and what happens, it dissociates partially, and that's why we put a reversible reaction to form CH3COO minus aqueous plus H plus ions, aqueous. All right? So it forms an acid, all right? But it's a weak acid that it forms. All right, so next, let's go down. So we're dealing with now reactions. We're gonna finish this one here pretty fast today. So reactions of alkanoic acids. What is the first reaction? One, let me just see if I could read this here. Aqueous solutions of alkanoic acids, page 143, reacts in a similar way to inorganic acids, such as hydrochloric acid, though the reactions are slower because the acids are weak. So they react just like hydrochloric acids and these other acids, but their reaction is slower because it's a weak acid. The hydrogen in the functional group can be replaced directly or indirectly by a metal and form a salt. The salts formed are ethanoic by ethanoic acids are called ethanoates. All right. So anytime you use ethanoic acid and it forms a salt, we just call it ethanoate. If it was butanoic acid, we will call it butanoate. If it was hexanoic acid, we'll call it hexanoate. All right. So that's the name of the salt. So the first reaction we have is reacting with reactive metals. So they react with reactive metals. And what happens when they react with reactive metals? The example we're going to use is ethanoic acid. It's just an example, and most of the times, generally, that's the example that CXC uses, ethanoic acid. But any acid can come, butanoic acid. Just remember, you have to represent the acid that is there. You can't write out ethanoic acid and think that is butanoic acid that you're talking about. All right? So one example, ethanoic acid, ethanoic acid reacts with reactive metal to form a salt and hydrogen gas. Okay, so example, we have calcium, which is a reactive metal in its solid form. I take a solid calcium and I drop it in some ethanoic acid, CH3COOH aqueous. And what is going to form is going to form calcium CH3COO in brackets and a 2. Let's call that calcium ethanoate plus hydrogen gas, H2. This is going to be aqueous. All right, and if we have to balance the equation, we'll put a 2 here, and the equation will be balanced. Okay, so in some books, you're going to see it written like this, CH3COO, and they put the 2 and they put the calcium there. The reason why they did that is to show you that the metal displaces the hydrogen. It takes the place where the hydrogen does be, and the hydrogen leaves as hydrogen gas, but it's the same thing, right? Just hold for me here one time. Just pause the recording. All right, so let us continue. All right, so let's move down. What is the next reaction that we have? So this was the first reaction that we have, it reacting with reactive metals. Another example of a reactive metal could be sodium, magnesium, all right, potassium. Those are reactive metals. The next one, they react with methyl oxides and metal oxides and metal hydroxides. So that's what happens here. So we're using ethanoic acid again, ethanoic acid. Ethanoic acid reacts with metal oxides and metal hydroxides to form salt and water. Okay, so first example, CH3. Well, let's find a metal oxide. Metal oxide, the example they have is magnesium oxide, solid, plus CH3COOH, aqueous, and we're going to produce a salt. In this case, it's just the metal displacing the hydrogen, and we'll know what salt is going to form. So in here, this case is magnesium. Magnesium will now carry a 2+ charge, CH3COO, and they have the 2 here, aqueous, plus hydrogen gas. We got 2 in front here, and the equation balance. And this one here is magnesium ethanoate. Right? So this is an example of a metal oxide reacting with an alkanoic acid. Then we have the hydroxide. We have potassium hydroxide, solid. Even it could be in an aqueous form. We could have it dissolved. Most of the times that's the case. And it reacts with CH3COOH aqueous to form potassium CH3COO. I put it like that because it doesn't need a bracket because potassium carries a 1+ charge, aqueous plus hydrogen gas. And that's supposed to be the equation there. It's balanced by itself. And this is going to be potassium ethanoate. All right. So that's that reaction. And the last reaction, well, that's just this one here. You have 2 more reactions to show. The next reaction we have is they react with methyl carbonates. All right. So example, ethanoic acid reacts with methyl carbonates to form a salt, carbon dioxide gas, and water. Okay. So, example of they use copper carbonate, solid form, plus CH3COOH, aqueous. That is going to react to form copper, carries a 2+ charge, CH3COO, brackets 2, aqueous, plus CO2 plus H2O. All right, so that 2 in front here, and it should balance the equation of well. All right, I think that should do it. All right, so let me check that carefully. Yeah, good. All right, so that balances the equation. So this is our next example of another reaction, reacts with metal carbonates. All right, everybody's following so far? I know you're moving now on a fast pace. Am I moving too fast for any of you all? Are we good?
Good, sir.
Nice. All right, happy to hear that. All right, so let us continue on this regard. Let's continue. All right, so the last reaction that ethanoic acids have, and that's what we're going to be touching in today, is they react with anhydrous. React with anhydrous ethanoic acid. So they react with alcohols. I'll write this out different than in the book. So one key point here to note is that in reacting an alkanoic acid with an alcohol, the alkanoic acid must be anhydrous. So 1, anhydrous, and that means water free. So that means the alkanoic acid has no water inside of it. It's alcohol free. So in this case, you are using ethanoic acid as our example. It can be any of the alkanoic acids. Ethanoic acid is just the example that they're using. With alcohols, and what forms? To produce and put here reacts with alcohols to produce an ester and water. All right. So because it produces water, we just call it a type of condensation reaction. All right, we just call it a condensation reaction. Why? Because water is being produced as a result of the reaction. So anhydrous ethanoic acid reacts with alcohols to produce esters and water. And this is the area that we're going to be going in today. Our topic as we go on from here is called esters. So we finished with alkanoic acids and we're getting into esters. All right, so let us see how well we can bridge and grow with this here today. So let's take out, for instance, I'm going to read the information here of an ester. But before we get into the ester, before we get into reading, I'm going to give you the general formula for an ester. And I want you to observe something. All right. So the general formula for an ester is CnH2n plus 1 COO CX, not N, H2X plus, plus 1. All right. So that is the general formula for an ester. It can be represented as this RCOO, and then you put an R prime here. All right. Remember what I said R is? R can represent any group of carbons, any amount of carbons, all right, a carbon chain. So if you notice what forms an ester is made up of two different molecules that link together. That is what we could observe. Even though esters are naturally occurring in the environment, as we read on, we're going to get to know more about it. Esters are basically made up of an alkanoic acid and an alcohol combined together. All right. And we're going to see that as we go down. So when you watch at the general formula, you can see the COO part here, which is actually the COO from a carboxylic acid. All right. So that you can look at, and you can think of it that the hydrogen there now is displaced by a carbon chain. All right. A whole carbon chain. That's what we look at, and that's what forms an ester. So here's my reading concerning esters. So 1, an ester is formed when an alkanoic acid reacts with an alcohol, or particularly an anhydrous alkanoic acid reacts with an alcohol. The reaction is a type of condensation reaction where two molecules join to form a large molecule with the loss of a water molecule. So, same thing as I was saying, all right? This particular condensation reaction is known as esterification. So the name of this reaction is called esterification. And what does it entail? That you have an alkanoic acid reacting with an alcohol. And what do we have? It's a reversible reaction, as you're going to see. And it's in the presence of concentrated H2SO4 and at a temperature of 170 degrees Celsius. Well, sometimes it doesn't matter, just a heat. All right, and take out 170 degrees Celsius. That is more like dehydration, right, of an alcohol. So they add heat in the presence of them, and what is produced? an ester and water. Okay, so an ester and water. So let's take a look at this reaction. All right, I think I would have given a class this note here. Let me just check something here. Checking to see how we progressed from there. Nice. Nice, good. All right, so let's take, for instance, I'm going to put out everything. I'm going to draw it so you could be able to see it clearly. So we are going to use ethanoic acid. So ethanoic acid plus, I'm going to use propanol. This is a reversible reaction. We have concentrated H2SO4 and heat. And we are going to produce an ester. And note the name of the ester. Propyl ethanoate plus water. All right. So one thing I want you to note here is that when naming the ester, let us name it a particular way. As you observe, once you know the alcohol, the name of the alcohol, and the name of the ester, you already know the name of the alkanoic acid. You already know the name of the ester. So in this case, as you can see, propyl, the propyl comes from the alcohol portion. So we call it the propyl part. And the ethanoate is the part that came from the ethanoic acid. So example, let me see if I can ask a question. So I'm going to pop this one, I'm going to call out Josiah. So Josiah, let's say that I have an alcohol called methanol, and I am reacting it with an alkanoic acid by the name of butanoic acid. So methanol, and it's reacting with butanoic acid. Could you tell me the name of the ester that is going to be formed? Josiah.
So methanate.
What's that?
I can't pronounce it.
All right. So if you notice the first one, right? The first example we had, ethanoic acid plus propanol, all right? And what happens is called propyl ethanoate, all right? The propyl came from the alcohol portion and the ethanoate came from the alkanoic portion. What would the name of the one that I gave you, what contains methanol and butanoic acid? What would you call it?
Butyl methanoate.
Huh?
Butyl methanoate.
All right, you may have a little error off there. Look at it carefully. What will be the first part of the ester's name from the first example? Where did that come from?
The butanoic acid.
No, look at the first example here. Propyl. Where did that come from?
Propanol.
Propanol. What is propanol? Is propanol the alkanoic acid? Or is it the alcohol?
No, sir.
So
The
what
alcohol.
is the alcohol? So the alcohol takes that first name, right? Right, Josiah? Right. So what is the alcohol in your example?
Methyl butanoate.
So methyl butanoate would be the answer. So you fully understand now, right?
Yes, sir.
All right. So methyl butanoate. All right. So all you just have to do for these, you have to just pause, hit it, be careful. Once you know the name of the alcohol, you don't even have to have the compound right out as yet. This is just one. Once you have the name, you could quickly get the answer. All right. So let's try someone else. So I'm coming down to Kishona. So Kishona, let's say that you have an acid. The name of the acid is called hexanoic acid, and it reacts with an alcohol called um, butanol. What would be the name of the compound? Kishona.
So like a
What you will call it?
so butanol. Well, I will take away the anol, so it will be hexo or something like that.
Yeah, I want to take your time. I ain't get answers yet. All I hear is something so. What is the answer? Take your time. It's not hard. It's not hard. Just take your time. What would be the answer?
No, butanol, not butanol itself, but buta or buta will be in front.
Mm-hmm.
I don't know how to pronounce the whole word, but no buta will be in front because they'll take away the anol, and
Mm-hmm.
then hexo acid will be added, but the acid will be taken away.
What
But
you
I
will
don't know
call
how
it?
to pronounce the whole thing.
What's the first one name? What's the name of the first one?
Hexanomic acid.
Right. But what's the name of this? Say this name here for me.
Methanol monate.
No, you see methanol? Take your time.
Met met metal. I don't know.
No, you're going right. You said methyl, right? So you're correct.
Methyl bromate.
Methyl what?
Bromonate.
Butanoate. All right.
Butanate.
Propyl ethanoate. The first one is propyl ethanoate. This is methyl butanoate. So what would be your second one? What would be yours? The one that is yours. What do you call it?
Hexic butanol. Yeah.
Butyl hexanoate.
Butanol.
All right. So you have to practice to say the words and them. Don't shy away from saying them, right? Not all of us is perfect, right? And but in the practice is where you get better. All right. So you have to push yourself out to say it, and you have to take your time and say it. All right. That's how you get better at things. All right. You don't get better overnight. It's about practice. All right. So don't be shy to do any of those things. And I'm happy that you at least take the chance. All right. So Nikela. So I'm pulling in Nikela now. Nikela, um, your question now, you have ethanoic acid and you have ethanol. What would be the name of the compound? Michaela.
Ethyl propanoate.
Repeat that again.
Ethyl propanoate.
Ethyl propanoate is correct. All right, ethyl propanoate is correct. All right, so let's go down. All right. So let me see if I could tackle in. I'm going to see if I can call Shaniqua, right? So Shaniqua, you have yours here. So Shaniqua, what would be your name of yours? Number 4.
Octyl methanoate.
Octyl methanoate is correct. All right. Octyl methanoate. Very good. All right. And I know Shanae waiting for this one here. All right. So I'm going to drop this one here, and I see like Akela, you give me some answers in the background. That's nice. All right. So Zane, this is for you. What
So
name? Pentyl?
pentyl decanoate.
Right, pentyl decanoate is correct. All right. So it's easy, as you all would see, to once you get the name of the alcohol and the name of the acid, it's easy to name it. All right. So now let's take a look here at the reaction itself. So we're going to look at the first reaction that I just brought out there, which was ethanoic acid and pentanol, and I'm going to write it out. I'm going to draw the structural formula. Let me just check the time as well, just to make sure that we make it right. So we're making good time. So in drawing the first one, which is ethanoic acid, we have carbon bonded to a carbon. This carbon here is double bonded to an O, single bonded to an OH. All right, you have hydrogens connected here. So I'm going to draw them in different colors, and I think I should have done that already. All right, let me see if I could put this in a red color to demonstrate what's going on here carefully. So I put this red here to represent nice acid. All right, and that is being reacted with the alcohol, which is ethanol. All right, so in this case was propanol, sorry. So 1, 2, 3. I'll put the OH on this side here. My hydrogens in. And we are going to produce. So what happens in this case of the reaction is that the hydrogen from the alcohol and the OH from the acid links together to form what we call water. That's what we call it, a condensation reaction, because water is produced. All right, and as a result, that causes a link between the two compounds, which result in carbon to carbon double bond O, and we have hydrogen here. So showing how the link O connected to C. H. All right. So here is where we have propyl ethanoate being formed plus water, H. right? Which is the same water that I said, right? That is being formed. So one, you can observe what happens in the reaction. So you should be able to do this with any of the compounds and them, this same reaction here. Let's take, for instance, let's look at the written form. So I could have put CH3, COOH, and it's reacting with C3H 3 times 2 is 6 plus 1 is 7 OH. All right. And they form at the end here CH3 CO O C3H7. All right. Form that plus H2O water. All right. And this is basically what happens. Right. In all the cases, we could see that and observe it. All right. So one, in all of these cases here, we have concentrated H2SO4 and heat. Concentrated H2SO4 and heat. Right, to make the ester. Right. So now the question is, what is this acid for? What does the acid work as? So one, get my black marker. The concentrated acid or the sulfuric acid is added for two reasons. One, to act as a catalyst to speed up the reaction. All right. And two, to remove the water produced during the reaction. This favors the forward reaction and increases the yield of ester. All right, so one thing to note here, what the acid here is used for. It is used as a catalyst and is used to draw out the water from the reaction and to favor the reaction now going to the right side. All right. So if someone has to go into A-level chemistry, you're going to see this. There's a principle we just call the Le Chatelier principle, and this covers it. This is it right. This is a big example of it right here. Esterification. All right. Because one, this reaction is a reversible reaction. Even though you see I put these arrows on top here, these arrows are not a representation of it, right? It's a reversible reaction. So I'm just correcting and make sure that you see that it's a reversible reaction. And once we have concentrated sulfuric acid and we heat it, it's going to, and of course, the alkanoic acid is anhydrous, doesn't have water in it, the reaction is going to go to the right to prefer to make the esters. If we have too much water inside the reaction gonna reverse and go back to the next side. And that's what we're gonna be getting into. But I want you all to note something here as I read. Many esters are found naturally. Those with low numbers of carbon atoms in their molecules are volatile liquids, which usually have a very distinctive smell, sweet, fruity smell. So let me give you an example. One, I used to love to pick guavas when I used to live with my parents. I used to love to pick the guavas in the yard. I used to pick them out from off a guava tree, and I used to bring them in this container and we rest it inside of the kitchen. After a period of time, you leave that kitchen and you come back, the whole kitchen smelling of guava. Really nice, fruity guava smell. Where's that smell coming from? All right. You're going to notice something about esters. Esters are volatile compounds as well. And volatile, which means that they do evaporate and they go into the air. That's why you're able to smell them. That's why esters are the ones that they're using colognes. They use esters. They get them from these trees. And if you notice here, is that one distinctive thing about esters is that they have this distinctive sweet fruity smell. All right? Sweet fruity smells. When I was in college, we were challenged to make the banana smell. So after we would have learned about esters, we were supposed to make the banana smell. From what you all know here is that esters, which these things that carries these nice smells, is made up of a carboxylic acid and an alcohol. If we can identify the alcohol side of it and the carboxylic acid side of it, I could get plenty of the carboxylic acid and plenty of the alcohol and then run an experiment with carrying out esterification and make the smell. So we had to do research and find out the alcohol that can be made, that can be separated from the ester that has the banana smell. So we found out the name of the alcohol because they would have isolated it in labs before. We learned the name of the alcohol. Next, we would have found out what is the name of the carboxylic acid portion that was found from it. And once we got that, we went into the lab and we requested our chemicals, which were the two chemicals that we have, and we carried out an esterification lab. And everybody, when they come up steps, they said, is bananas all you have there? Everybody was smelling the smell of bananas. All right? Because we had our esters and we had them heating to produce the esters, and the smell was coming out of the lab. Went into all the corridors and the entire lab area, and the lab building was smelling of bananas. Why? Because of what we would have done. You have a foot in the door. You understand now what esters are made up of. All right? And now you can be able to identify them around us. There's a flower by the name of Lady of the Night. It only releases that smell during the night. It's an ester. Pineapples in the kitchen, when you're resting a pineapple and you leave it to ripe for a time, you will smell that same pineapple smell coming into the air, but you're not even close to the pineapple. Same ester again. All right? So note that esters, the ones on them that have a low carbon number of carbon atoms, which is the short chain ones, even just like the ones that we would have done here, the short chain ones, they are volatile liquids and they have a distinctive sweet fruity smell. Once we find out, we know it's the short ones on them. Note this next one. Page 144 in the concise. They are found especially in flowers and fruits. Flowers and fruits. I smell my roses on them this morning, and they were smelling lovely as well. esters. All right. Now, animal fats and vegetable oils are esters formed from fatty acids, which are long-chain alkanoic acids, and glycerol, which is an alcohol. So we're learning something here today. Fats, which is coming from animals. So if you go and you're accustomed cleaning chicken and you see the fat on the chicken, that is an ester. All right. What else? The fat on any animal, whether it be lamb, pork, whatever the case may be, they are esters. They are long chain esters. Then you ask the question, so why do those smell sweet? Because the sweet smelling ones are the short chain ones. These are long chain ones. And the long chain ones not necessarily have a sweet smell. All right. And especially when you're dealing with meat, you have other things to talk about, other things that you're dealing with. All right. But generally, when we have fats, the fats on them don't generally have a very bad smell. Meats tend to have it because they're dealing with flesh as well and other components. But if you isolate them and you're able to isolate them pretty well, they don't necessarily have a very bad pungent smell. All right. People tend to cook with lard, which is pork fat. All right. People also cook with some other fats from animals when they want to make broth and stuff for them, and it's not necessarily a bad smelling thing. All right. So so let's take a look here. So I'm going to bring an example here. They would have talked about fatty acids and glycerol. So I'm going to draw out a molecule of what a glycerol looks like. So a glycerol contains 3 carbons, and they have 3 alcohol groups on it. This is glycerol here. All right, on the next page. So some persons might say, oh, that's propyl triol, right? Yeah, you can say propyl triol, all right? I could understand why you would call it propyl triol, all right? Or propan triol, sorry, all right? So, but this is called glycerol. So glycerol. And glycerol can link up with long chain carboxylic acids. So example, I'm going to bring one which is 7 chain longs, which would be heptanoic acid. And I'm going to put it back to front here. I'm going to draw it red. So heptanoic acid is going to be C double bonded to an O, and you have the OH here. So C was 1, 2, 3, 4, 5, 6, 7, and I put my hydrogens here. H, 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 H. Nice. So we have the 2 of them here. This is heptanoic acid. All right. So the heptanoic acid and the glycerol, they can link. But note this, they said 3 acids. All right. 3 long chain acids. And we refer to them as fatty acids. Okay. So there's actually 3 of them. So let me see. I'm going to bring back some knowledge. I like to use things that we do already before to try to apply them here again. So you could see that you could apply them in several areas. So I'm going to connect the glycerol and the heptanoic acid to make my fat or my lipid molecule, right? So I'm going to erase here. I'm just going to connect them. All right, I'll just connect them like that. Okay, it's a long, I don't want to draw it over again. All right, so I'm going to erase the other hydrogens now and show them connecting to other, well, same like heptanoic acid, but I'm going to draw them differently. So I am going to draw the condensed version. So the condensed version would be C and I have CH2, CH2. So that's 1, 2, 3, 4, 5, 6, 7, CH3. It's the same thing above. So everything going to be heptanoic acid. I'm just drawing them differently in the way that we would have learned them. So this is the condensed formula way that I drew it. All right. Let me draw the next one, same heptanoic acid, but I'm going to draw it in the line structure. So I'm going to connect here, here, double bond O. So that's 1, 2, 3, 4, 5, 6, 7. All right. So just for a recap of what we would have done in this area here, if you remember when we did the line structure, I was telling you that the angles are carbons. So that is 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, 6 carbon, and the end here, 7 carbon. They represent carbons and the hydrogens are understood. We don't draw them out. They already understood how they are. All right, this is just a little recap. So some you will see these examples coming up sometime, and I just wanted to be aware of them. Okay, so let us go down. So that's an example of, and these are what we call the fatty acids. So these here, right? Which are alkanoic acids. Okay. So what are we going to hit on next? What is our next position? All right. All right. So let us take here, for instance. So we learn about esters. We learn how esters are formed. We are going to look at how esters can be separated. So if I get an ester, remember I was telling you that we were making bananas and I had to find out what was the alcohol that made up the banana and what was the alkanoic acid that made up the banana smell. How did we know that? The persons and them had to be able to separate them in order to figure that out. What process did they do in order to separate them? The name of the process that we're going to be looking is called hydrolysis or hydrolysis. And I told you that we would be talking about that again. Hydrolysis or hydrolysis. All right. So we're looking at hydrolysis of esters. All right. So I'm going to hit the pause here. Everybody, how you doing? I'm just checking in on how you doing. You all doing good? Just checking in with everybody. Toby, you good?
Yes.
Nice. Kishona, you good? You holding in?
Yes, sir.
Nice. Zani, I know you should be holding in strong and nicely there. All right.
Yes, sir.
All right, good. All right, Josiah, I know you should be there. Akila, I know you should be happy to see that you're still here. All right, even though I'm recording. All right. So let us see if we could continue. So we're looking at hydrolysis of esters. How do we separate them? We separate them 2 ways. Well, there's one way, but there's 2 things that we can do. Let me just read here. During hydrolysis, a molecule of a compounds are broken into smaller molecules by reacting the compound with water. So how do they separate hydrolysis? With hydrolysis, it's basically water you're reacting the compound with to separate it. So hydrolysis of an ester can be carried out by heating the ester with a dilute acid, note here, not concentrated, a dilute acid and an aqueous alkali. A dilute acid and aqueous alkali. So, two ways. One is with an acid and one is with an alkali. So, how we separate them? We call one acid hydrolysis. So let me put that in red. Acid hydrolysis. And that is when we use acid to separate. So in this case, this involves heating the ester with hydrochloric acid or sulfuric acid. All right. So the acid is the catalyst. Remember, is water is the real thing that doing the job. The products are an alkanoic acid and an alcohol. Right? Those are the products that we have from an ester. And this is, let me put from an ester because we could use hydrolysis to separate other things from an ester. So let's take an example. So we're going to give the example. So again, they have the ester, which is the same propyl ethanoate that we had. So CH3, COO, C3H7, all right? And that is going to be a reversible reaction, of course, to produce CH3COOH plus C3H7OH. So here is propanol, and here is ethanoic acid. All right. So let me see if I can erase it because I have to put water here. H2O. Sorry. And of course, I'm putting an H plus here because we can use either hydrochloric acid or sulfuric acid, and H plus being present or H plus ions just basically tell you an acid. So now just put H plus ions, it could be any of the acid. Okay. And here, of course, it was propyl ethanoate water. All right. So that is what the case is here. All right. Now we're going down to the next one. And the next one is the real one. Reason being because of this particular reaction, we have it being applied in some instances. We will not go through it today. All right, we'll go through that by next class. So just checking the time, or hopefully we can get to go through it today because we're running fast today. We might be able to just stop on some areas here. The next one we're going is alkaline. So that is blue. So we can just do a little recap today. Alkaline hydrolysis. Now, what does this one involve? It involves heating the ester with potassium or sodium hydroxide. Okay. The products are the potassium or sodium salt of the alkanoic acid. I'm gonna let you all see that. And the alcohol from formed from ester. All right. So alkaline hydrolysis. So remember, hydrolysis is basically using water to separate this compound. And in the case of the alkaline, we have something different occurring. What's the difference between the acid hydrolysis and the alkaline hydrolysis? They have a product, both of them breaking apart the compound. Both of them are achieving the compound being broken apart. But the products are different. One is going to have the alkanoic acid and the alcohol, sorry. And the next one is going to have the salt of the alkanoic acid. So it's going to make a salt instead and an alcohol. So the next one is not a reversible reaction. The next one is not a reversible reaction. The one which is the acid hydrolysis is a reversible one, but the alkaline hydrolysis is not a reversible one. So let me show you where that is concerned, because this reaction does actually occur in stages. So I'm going to write out the full reaction first, and then I'm going to show you the stages of the reaction. So in the first reaction, we have the alkanoic acid. Sorry, not the alkanoic acid, the ester, which is the same propyl, CH3, propyl ethanoate, COOC3H7. And it's going to react with, let's use sodium hydroxide. And we get an arrow here. And it's going to produce CH3COO, and let me put sodium, and ACH3COO plus C3H7OH plus the alcohol. All right. So let me show you the 3 steps of this. So the first step, remember, water is the one that does the separating. So one, you have the CH3, COOC3H7, which is the propyl ethanoate. And it's going to be split by the water. It's going to be held. Now, this happens in the presence of the sodium hydroxide, which is basically helping to catalyze the reaction. And then what forms the carboxylic acid? CH3COOH plus the alcohol, C3H7OH. All right. So everything there is aqueous. Everything is, well, this is going to be liquid, right? Liquid, aqueous, all right? But you could always look at that afterwards, all right? Now, what happens here, the second stage, if you notice that this is an acid, and this sodium hydroxide here is a base. So the moment the alkanoic acid is produced, because sodium hydroxide is present there, it's going to react with it immediately. Everybody understanding me? So this first reaction is going to go. That's going to happen first. But because this acid is producing a reaction, every time it's produced and it's in the presence of a base, immediately it's going to now react with the base. And reacting with the base now, which is CH3COOH, reacting with NaOH, is now going to form CH3COO. Well, let me erase this. NaCH3COO plus water, H2. All right. And this is your twofold reaction. That's the two steps of the reaction that's going to happen. All right. And that water, of course, is going to help to react with some more of the split more of the what you call it, the ester into and that reaction keeps running over and over again. So that's why they just put it in this form here. This reaction above is the real one. Okay, just straight one time. All right, anybody doesn't understand? So everybody is good there. All right, 7:45. Now, I am going to hit this pause button on this side. I have to hit the pause button because I'll be going into another area which is called saponification. And that is going to head off in us heading close to close off organic chemistry because we are almost complete. And I'm anticipating by next class, God's willing, we would be able to complete organic chemistry. All right. When we are complete, I will not be doing this lecturing or this teaching part like I am doing here now. We are going into some past paper questions. So the usual stuff that we have when you come to class, you're going to be prepared to do some, well, you have some work to do. All right. You have some work to do. And that means that I'm going to be highlighting some past paper questions for you all. You're going to organize the past papers and then I'm going to tell you what questions to do. And then we come to class and we address them. I would go through them and you all will get to get those answers cleared up in that first class, in that first specific class. But before we do, let's take a general recap of what we would have done today. All right, just a general recap. We're going back up from where we had here. Let me see if I can scroll up. When we would have talked about alkanoic acids. All right. So we'd have talked about alkanoic acids and we would have gotten some information. All right. So one, we know alkanoic acids, we know the general formula. We know we have to remember the general formula. We need to know our general formulas for our homologous series. We need to know them. Next, we would have known, we would have talked about how the alkanoic acid was polar in nature and why it was polar because of the OH. So I'm going to see if I could pull in some questions here in the meanwhile. All right. So we know that it was the OH group. So there are some things that we need to get. So could somebody tell me what volatile means again? When we say something is volatile, what do we mean? When something is volatile, what do we mean by it being volatile? It's going to take that one. Nobody's not going to take that one? Let me see if I could pull in Cook. Akela, since you are here then now, could you tell me what volatile means? Right, so I'm not getting Akela. What about you, Josiah? What is volatile? When you say something is volatile, what we mean?
So, I mean, I remember it correctly, so, but I remember it being is that it change on temperature.
It changed from a what?
It does change, easy to change with the temperature applied to
Right, when you say change, what are you changing from?
stated things.
What is that?
It
All right, so I get clearly there. All right, so if you're saying changing from a liquid to a gas, then you're correct. All right. So changing from a liquid, how easy something it is to change from a liquid to a gas. All right. So in other words, how easy, well, basically, that's it. How easy it is, the ease of it to change from a liquid to a gas. That's what volatile is. All right. So next question, let me see. Kishona, why are alkanoic acids soluble in water? So coming down the line. So I'm just picking as a coming down. Why are alkanoic acids soluble in water? All right, so I'm not getting Kishona. Shaniqua, why are acids, so the alkanoic acids, why are they soluble in water? Or how? What makes them soluble in water?
Because of the OH ions.
All right, not the OH ions, but the OH group, the hydroxyl group. So you are correct because of the OH or the hydroxyl group. All right. You could tell me what exactly about it helps about that hydroxyl group makes them soluble. We're looking for a word that would help you there. Why does it make it soluble? I just want to push a little bit.
The polarity.
The polarity. All right. Nice. You are correct. The polarity. All right. So we know talk about OH having a polar nature, oxygen carrying a negative charge, the hydrogen carrying a positive charge because of the electronegative oxygen. All right. So nice. So moving down, we would have done some other things. We would have talked about reactions of ethanoic acid. So ethanoic acid, before we go on, why do we call it an acid? Janae, why do they call it an acid? Janae. So I'm not getting Janae now. All right. Cook, you still there with us? You know why that's called alkanoic acids? So I'm pulling down. The reason why they are called acids is because they partially, go ahead. Somebody else coming in there?
Akela.
Akela. Yes, Akela.
So that have carbon double bond.
Mm-hmm. Carbon double bond to what?
Oxygen.
Right, it's double bonded to an oxygen. Why is it an acid? So this is the part that I want you to get here. This why it is an acid. It partially ionizing in water.
Because I can't say the word.
Or the
Carboxyl.
Mm-hmm.
So that all again in my head right now.
All right. So the carboxyl group has a hydrogen in it, and it can release that hydrogen. It partially releases that hydrogen when it gets into water. Partially releases it. That's why they refer to it as being a weak acid. So because it can produce H plus ions. All right. That's why we call it a weak acid, because it produces H plus ions. All right. That's why. All right. All right. So we're looking at reactions. What's one reaction of the ethanoic acid? Josiah, one reaction. If you could do one reaction, so we're coming down. One reaction of alkanoic acids. What do they react with? All right, Kishona, please let me know that today. What do alkanoic acids react with?
Still no water. I think.
No, not water. All right. As Josiah said, they react with alcohols. All right. So he's correct that they react with alcohols. All right. They react with other something else. What else do they react with? So you're going over everything. We're just reviewing what we would have learned. Shanika, what do they react with?
So you can repeat the question, please.
What do alkanoic acids react with? So Josiah said alcohols. They react with alcohols. That is correct. What else do they react with?
Metals.
Right. And particularly not just metals they react with. What type of metals? Reactive metals. All right. All right.
Yes.
So they react with reactive metals. And you are correct as well. They do react with metal oxides as well. They react with metal oxides and what else? What else?
Metal hydroxides.
And metal hydroxides. So very good. So far we have them reacting with alcohols. They react with reactive metals. They react with metal oxides, and they react with metal hydroxides. And what else do they react with? Zane. Let's see if Zane come back there by now. I think Miss Gray probably going and sleep, man. Or Miss Gray step out. All right. So what else do they react with? They have one more. One more thing that they react with, alkanoic acids. All right, they react with metal carbonates. All right, so we would have just coming down with everything that we have there. They react with reactive metals. They react with metal oxides and metal hydroxides. they react with metal carbonates, and they react with alcohols, as Josiah would have stated. All right. In reacting with alcohols, they produce what we call esters. All right. Please remember the formula, the general formula for esters. And when the ethanoic acid react with alcohols, we call that process esterification. All right. So I'm going to hit the pause button here for now. I want you all to please go over the stuff on them that we would have learned here today, including that of alkaline hydrolysis and acid hydrolysis. We're going to be applying them again into the next area, which is what we call a soap making. All right, saponification and stuff like that. So I implore you guys to do your best to keep yourself sharp. Right now is the time where you're gonna be putting in a lot of work. All right, keep putting a lot of work right now. You gotta keep putting in the work, and eventually you just have to keep at it. Just keep at it. The time is going to come to an end, and you will reap what you sow. You will reap what you sow. All right, so make sure that you sow some good seeds so that you will sow good seeds. All right, so I'm going to pause there now. I'm gonna call up George for this time.